So today we start a new topic on soil and structure interaction, which will lead later to foundation design. This is an interesting topic in the sense that it lies on the boundaries of structural engineering and geotechnical engineering. And sometimes both sides do not understand this well because they do things one way. Geotech, we do things another way. And then we assume something from their side, they assume something from our side, and somehow this interface is not well managed. I know in your model, in your project also, when you model a frame or anything, normally you see that you draw a short line and then you put the hash and you say fixed or pin. And then you forget about there's a whole thing below the building. And then we just ignore it and we just say, oh, my structure ends here. I don't know what happens after that. And then you calculate the load and then you apply it to the foundation and then you remove the structure as if the structure doesn't exist and you design the foundation. And that's just not how it is. Reality is that the structure, the ground, the soil below that, around that, all side, all the way down to the rock is one continuous system. There is no break, but we make this artificial division between that and then we make some assumptions. So we try to see how far these assumptions are good or not good and what we should or we should not do. So let me start with a very long time ago. That means my first or second project, some 45 years ago, when I joined the consulting office as a junior structural engineer, they asked me to do a project like this, a portal frame, and then asked me to analyze it and design it. And as you can imagine, at that time, I draw this figure and then I put those red lines below that. And I said, okay, this frame is fixed and I will design it like that. So I started the design and then I come up with the load on the foundation and I come up with a very large moment and very small axial load because the load is small. It's a steel frame, very light, but the moment is very large because it's a portal frame. And then, so now the problem is that when I try to design this foundation, I just cannot design it because the moment keeps causing the large soil pressure on one side and uplift on one side. So I keep increasing the foundation size until it went outside the building, the site limits. It becomes so huge. So I took that foundation to my supervisor and I said, this is funny because it's a small building, just one story, and the footing is so huge. Nobody will make it. People will think I'm crazy. So this started me thinking that something is wrong between, I said, and then my boss at that time, he said, okay, why don't you change the fixed foundation to pin foundation? And I said, oh, that's a great idea. So I changed it to pin foundation and suddenly moment is zero and I get a very small axial load. The footing is now so small that it's almost the same size as the column because there's nothing there. So two extremes, just by changing the foundation option or foundation assumption, it completely changed the whole foundation design from very huge to a very small footing. So it's quite obvious that both of them cannot be correct. The answer has to be somewhere in between. Just because I draw a small hinge didn't change the structure. The structure will remain as what it is. It's just my assumption that made this change. So the reality is not changed just because I changed my assumption. So I kept thinking about that a lot, and I said, this is not right. So when I made the drawing, I actually designed a hinge at the base of the column. It is a concrete structure, not a steel one. So I designed a hinge connection between the footing and the column to make sure that I construct what I have assumed. And it was not usual for people to see a hinge detail in concrete column because I brought the bars and crossed them so it will crack and create a hinge there. And people were making fun of me that, what are you doing? We take the column bars all the way down and you are crossing them. And this will crack. I said, yeah, exactly. I want it to crack at the base so that it will perform like a hinge. So two things that I learned from that long time ago. One is that we should construct what we model. Our assumption and our reality should match. We should not try to model something that isn't there or construct something that we didn't model, because then your results will not be compatible. And second is that I learned that this foundation, assumption is very critical. So that's then second thing that I learned at the same time was that when I asked the bearing capacity calculation, allowable bearing capacity from somebody, and I look at this formula, I think that there is Agi or somebody, and I look at so many things in that formula, and I realize there is a factor which relates to foundation size. So the bearing capacity depends on the size of the footing and depth of the footing, which to me was, at that time, I didn't really understand, because I thought it's a constant number. So whatever footing because I'm going to size the foundation based on the bearing capacity. And if the bearing capacity itself depends on the size, then what's the point here? So most of the geotechnical consultants at that time just used to give one single value of the bearing capacity, and people just use that blindly. But when I look at the formula, I said it can't be true. The bearing capacity must vary with the footing size. So the geotechnical people should give me a range of bearing capacity, not one single value. So I went back to the geotech guy and I said, what is this? And then he said, yeah, you're right. And then he gave me a curve graph between the foundation size, foundation depth, and the bearing capacity. And he said, you can use this one rather than a single value. So I learned two things at that time from this thing, that the structure's response, foundation size, bearing capacity, they are all interrelated. There's an interaction. We cannot separate them from each other. Okay. Because this is the real footing that you actually see. The footing has a size, has a depth, and that is reinforcement on all and their column. It is not a pin, it's not fixed. It is something embedded in soil which will deform and which will, depending on the soil and many things. So the two are going to interact in multiple ways. So it is none of that, not this. It's something like that it is kind of a spring. The footing is kind of sitting on soil springs, and it's also restrained by the soil from the side by a spring. So this is something how it will look like. And you can convert that into three springs, two translational springs and one rotational springs. The rotational springs will represent the rotational capacity of the footing, and vertical, and horizontal. So there are three springs minimum needed to replace a footing. So this three spring concept is the one that at that time, I thought, oh, this is great. But the problem is calculating the rotational spring is not easy, right? And then putting them in, I had no software at that time. Actually, I was developing my first frame analysis program. So I thought, okay, if I develop the program myself, how can I incorporate this thing there? And I studied and I couldn't find a spring element, or I couldn't implement the spring element. So I put a frame element like this one at the bottom, and I put several columns below that, and I put a horizontal column on this side, and I make their size so small that they start to act like soft springs, because you can vary the axial stiffness of the column to make an equivalent spring, because it's just a spring. So I used columns, multiple columns under the footing, and set their EA over L in such a way that it starts to represent the soft soil. So ultimately, I was able to model this at the very minimal software, stuff, using some kind of a formulation and assumptions long time ago. But things haven't, so this is the right way to do that, or one right way to do that. Now, if you go to ETABS or SAP, I did the same thing with SAP recently. Of course, now it's easier. I can make that frame, and I can make the footing over there, and I can assign the soil spring value or K value directly to the footing shell elements. And the program will calculate the point springs and distribute them everywhere. So which means that now it's almost no brainer, no effort at all. All you need to do is you take the column down, you put the footing as a shell element below that footing, model the footing also, and assign the area spring under the footing, and then SAP will do the rest. So the same thing now has become significantly easier to do that. Despite that, many people don't do it. and which is so surprising because it's almost takes no extra effort to do that. But I still see hundreds of buildings coming to us for review, whatever, not doing it. And I'll show you some of those things. So now it's very easy to do that. So you just can see that now there is going to be a rotation at the base. Small moment, there's a rotation. It's not zero. It's non-zero. So it's neither pin, it's not neither fixed. You get actual vertical displacement, which you can calculate the settlement. You get actual rotation, and which will reduce the bending moment. And you actually get actual horizontal displacement, which is related to the lateral restraint. So now getting the structure and soil to interact together, at least at the simple level, it should be no-brainer. No, this should be very easy. And everyone should be doing that. Okay. So that's where we are at this point. Next, another problem, same time, similar, very long time ago. Engineers at that time used to have this idea, and still have, some people still have this idea, that we should design our building for 1 inch differential settlement. And I kept hearing from every engineer, every senior, that, oh, you must check your building or design your building for 1 inch. I don't know where it came from, 1 inch differential settlement. And I said, okay, but how do you do that? And what does it mean that you have 1 inch differential settlement in the analysis? So basically, the idea is that if this is a building, you're trying to pull one of the columns down by 1 inch to design for differential settlement. That's the only way to do that, right? So you would assign a displacement of 1 inch downward to one of the columns, differential. And I said, okay, let me take a look at what happens to the building if you try to some, forces under the ground are pulling the column down, or somebody is, some aliens are pulling the column down into the ground by 1 inch. If it happens, what will happen to the structure? So let's look at that. So I did that. If you do that, you get this kind of deformation in the building, right? Because you're pulling the structure down by 1 full inch, which is about that much, right? And then if you look at the bending moments, I got a positive bending moment of 280 kilonewton meter here instead of the negative bending moment that you should get over the support, because the support is no longer a support, it's a negative support. So which means it's pulling the beam down. So you get a positive bending moment instead of the negative moment that I was getting. And it was 280 kilonewton meter for this. And it was more than the capacity of the beam. So I increased the beam size because I can't design this beam for 280 kilonewton. And as you know, stiffness and deformation are related. So when I increase the size, moment become 910. It didn't help at all, because the moment I increase the size to design for that 280, the moment become 910 because the beam is too stiff. And if you do the same 1 inch deformation, it will now generate much larger bending moment because of the K and stiffness. So this is, and if I design for 910, I will get 5,000. So there's no way that I could design this structure, simple structure, for 1 inch deformation or 1 inch differential settlement, because the moments will be totally, and shear especially, will be totally unacceptable. And we can't design it. So people keep saying that, but I don't know how many people actually try to do this and find out what happened to their structure. Because this is a simple frame, nothing complicated. Okay. So once again, the question is, then I asked the people, why are you trying to do this? Oh, there could be a weak soil spot in some foundation, so that foundation may settle more than the other. Once again, you should let the structure decide how much it wants to settle if there's a weak soil, and how much weak can it be, right? So we started doing at that time parametric soil modeling. That means design the foundation for multiple spring values, because you don't know exactly what the foundation is, the spring value is. So you try many. And I found that the structure's response is not so sensitive to the value of the K, but it's very sensitive to rigid and pin. In between, K can vary by 2-3 times. The response doesn't change that much. So looking at that, we come back and I said, okay, let's see that this soil is all equal. Same weak, little bit reasonable normal soil. And I found that the settlement in the soil was 21 millimeter. Natural settlement of all the foundations was roughly 21 millimeter based on the load and based on the soil properties. Now, let's say one soil that you're trying to say is very, very weak, half the strength. Normal bearing capacity is 1 ton. Here it's only half ton. It can't be less than that, right? So I said, okay, fine, let's try that. And I found that the difference is only changed to 28 millimeter, right? 23 millimeter, this one. So what happened is that this changed from 21 millimeter to 23 millimeter, 2 millimeter more, and this one 28 millimeters. So net difference is only 5 millimeter when the soil is less than half the adjacent soil, right? Because the structure, as soon as it becomes soft, the loads will start to distribute to other members, and then load on this column will actually reduce. So you cannot assume the same load that was coming earlier on this column, because it will now be taken up by the other people, because this guy is going down, other will try to pull it back, right? Because of the structural stiffness, it will be redistributed. That's why this column increased by 2 millimeter, because it now carries more load than before, because it's trying to help that guy who's failing, right? So maximum in this case, I found that you cannot have more than 6-7 millimeter of deflection, even in worst soil condition difference between the adjacent columns. Okay. And then when I go back to the bending moment, compared with that one, I only got 62 for that case, right? And 62 was easily manageable. So 280, if I use one inch, which cannot be managed, I increase size, I get 910, which definitely cannot be managed. So what I got actually was only 62 for the soil, which was very weak. So the third lesson we learn is that the differential settlement, specified differential settlement, is a myth. It should not be enforced. We should let the structure and soil tell us what kind of deformation is practically possible. In fact, when the building gets taller, many frames, you can even remove one column, nothing happens, because the Virendale effect and all of those effects will just take the forces elsewhere. Getting rid of one column is absolutely, it's not going to collapse anything. So that's how the soil structure interaction is important in handling the differential settlement. So we should actually try to compute differential settlement by varying the soil properties rather than enforcing the predefined differential settlement, which is impossible to do anywhere, right? Because you can't pull the structure down. So you have to let the structure settle. So to let the structure settle, you need to change the soil properties. You can play many scenarios, but you let the structure decide what's going to happen with that. So that's the lesson number 3. So first lesson is that you have to, the foundation loads and structure moments, they are interconnected, and soil structure model will tell us the right ones. The other one is that soil bearing capacity is actually related to size. So you need to get the correct bearing capacity in the first place. And third one is that we should not specify the direct settlement on the structure. Now let's go to a slightly bigger problem, and that is basements and embedded structures, which is almost everywhere. Every building has a basement. As soon as you do that, you come to this situation. And this is also one of my first projects. Common is to have 5-story, 6-story buildings in commercial zones, and do a couple of basements. So this is a very common problem, common structure. So now, as you can see here, is that as soon as you go down, there'll be soil pressure, active soil pressure onto the structure when the structure is still, which is easy to calculate. You use whatever formula you have, and you can design the basement walls and all. But when the wind or earthquake, especially when it will come, then it will deform the structure on that side. So now on one side, the structure will try to move away from the soil, and one side it will push against the soil. So two things will happen. On one side, passive pressure will increase because now structure is pushing against the soil. So the soil is now going to react. So now it's going to create additional pressure on this side. And one side, there might be separation between the soil and the structure, depending upon how much deformation is there, right? And because it's an earthquake, it's going to go like that and like that and like that. So both direction, you might have soil separation between the structure and the soil, and you also will have excessive pressure. And the pressure generated on this side will be inverse of the triangle pressure, because on the top, it will push more, and as you go down, the push will be less, so pressure will be less. So that means that increased extra pressure, where initially it was zero, will be large. So now suddenly you have a very different soil pressure profile because of the lateral movement or lateral forces on the structure. So that's the first thing that we need to know. Once again, we need to do, and this is given by ASC, how much is the extra pressure? There's a formula to calculate that. Right? So they have estimated how much you will get depending on the soil type and all of that. So you get that. So you can estimate the extra soil pressure like that. So, but this is not the end of the story. Look at the plan. The plan is typically buildings are very long, front is small, and buildings are deep, right? So when the earthquake force is coming in this direction, the whole building is trying to move this way, and only this short wall is resisting all of the force, right? Total mass multiplied by whatever factor, you have a lot of force coming to the building. It's moving like this table is moving in this direction. So only this wall will get all of the passive pressure. But there's also friction between the soil and the walls of the basement on the longer side. So that friction will not let the wall slide freely because soil is connected to that. There's a lot of friction between them. So which means that actually the force may not even reach this front wall, because the side friction, depending upon the type of soil and type of construction, may just lock the whole building and nothing will reach, or some will reach there, some will reach the side walls. Almost no one that I know typically models soil friction on the sides. They just go straight away and put the springs on that side. But the situation is very different when you push the same force pushing on the longer side. Earthquake force is the same in each direction. So when you do that, then the whole building will immediately hit that one, because the side walls are small. They will not have that, the friction will not develop. So then you have the pressure developing on those long walls immediately. So this geometry, the shape, the length, other things, they will govern a lot on what kind of pressures are generated on the wall and also on the soil, on those sides. Okay? Very different behavior. But things get more complicated, or not, I should say more interesting. In reality, things can be like this. There can be a building, next to that there's another building, and mid-height, not the same height, right? No gap. Sometimes they just construct next to your building, right? In most countries, they're constructed like this. In Myanmar, they have a law that even if your buildings are like that, you have to have a gap of how much? 30 centimeters in between the building, 1 feet. Must be separate. 1 feet, 30 centimeters. So, but so that is perfectly fine. But here you can see that now on one side, the other side, the condition is no longer the same. One side you have the soil, another side you have another building, and the building also may be a different height. So now there's a chance of pounding, right? The structure will actually hit the other building if they're very close. If they are even touching, they will separate. So actually, we did a thesis on this issue, that what happens if the buildings, 5 or 6 buildings are connected together and they behave as one with no gap, and what happens if there's a little bit gap, So it was interesting to study, doing the full nonlinear dynamic analysis to figure out what's happening if you have a block of buildings built side to side, not fully connected, but adjacent. So we put the gap element there and they do all that kind of stuff. So that study was interesting to find out that how the buildings can support each other if they are completely connected together without gap, same floor level. But if there's a little bit gap, actually it's not good. Big gap is fine. Okay. So it's that the small gap is the worst. Like 1 inch, 2 inch gap is the worst. Either you just cast together or you have a gap big like in Myanmar. Okay. So now then look at the plan. Also possible that the next building is only halfway, not the full way. Anything can happen. So which means that you cannot make any reasonable assumption about the foundation, because today it will be like that. Tomorrow somebody will come buy that land and start constructing, and it will change your assumptions of your basement design altogether. So engineers are at a loss what to do. If you include it because the soil is there and it in the future isn't there, and if you don't include it and the soil, either way you are in trouble, because there is no simple answer how to handle situation like this until you do a few scenario-based design. But if you're doing a small building like that, you're probably getting paid very, very little. You hardly have any fee to even do the basic design. Forget about all this scenario-based stuff, right? But the complexity is like that. And when the seismic force, earthquake wind comes, it will exploit all these things immediately. It's looking for things like that. Eccentricities, uneven supports, these will become the primary targets of earthquake to concentrate the forces and do all of that. So we can't do it on one end, but that's where the damage will come from. Okay. So I'm just trying to raise some of the issues that you should be aware of, and depending upon how you should at least know what's going to happen and how to guard against both of them. Same is the case of the stability and all. Okay, now coming back to the level of complexity, even for a simple foundation, forget about complicated buildings. Let's get back to a simple foundation and a column embedded. So here is a pile or a column in the soil, and it is only subjected to axial load, the first one, A. And in that case, it's easy. There's no problem at all. So if you apply a load on the column like this or a pile, one of the two things can happen. One is that the soil is very weak in friction, or the pile is cast in place. So the end bearing will only support it. So all the force will go down to the end, and then you apply the load, vertical reaction will be here. Soil is not participating much. Second is it's a driven pile. So that means you're driving it by a hammer. So that means no force will reach here. All the force will be taken up by the friction, because friction stopped it from moving down. So there's no force at the end. So there's two extremes: all the force at the base or no force at the base. All the force by the friction or no force by the friction, or something in between. So vertical load in the soil will be shared by end bearing and skin friction, depending upon the soil and the driving method or casting method of the pile. That's for a very simple situation. Come pile and bending moment. Now, suddenly the situation will become quite complicated, because the bending moment will try to bend the pile on this direction, and then the same thing. Lateral forces will try to resist on one side, separation on the other side, and then depending upon the stiffness of the pile and the stiffness of the soil, either if the soil is very weak, the column will just bend. If the soil is very strong, it will restrain the column will start to bend like this. So depending upon that, the behavior or interaction between them can be very, very different, very different. Okay. So most people believed or still believe that after a certain depth, H1, the pile will become locked by the soil, and it can be considered that at that point, it's a fixed condition. So you move the pile fixity point from here to here, rather than fix the pile here, you fix the pile a certain depth below that, where you feel that the pile cannot move anymore vertically and horizontally. And that depends up to 5 times the diameter of the pipe, three times the diameter of the pile, depending on the soil. So about roughly 5 times the diameter, you can assume that the pile has locked, has stopped moving, and then that's the location So that's the effective length of the pile, and that's where the moment should be calculated, not at the top of the pile. So that's the simple case. Then sometimes often we have piles, group of piles with the pile cap and several layers of soil. So now you can imagine the things getting very complicated, not just one soil. Every layer is different properties, and you have multiple piles close to each other with the pile cap, with a column on top. The whole system suddenly becomes pretty complicated. And it's very hard to see how it's going to behave until we model it completely and correctly. And then you have another case, you have a simple column, you take the foundation down and then you fill it up again. So whether the soil is holding the column or not holding a column, whether the footing is free to rotate, what about the weight of the soil on the top of that? What is that doing? What is the pressure it is doing? So the whole system suddenly becomes, not easy to see how it's going to behave. And sometimes you have large column here, you have a floor slab close to that. What's going to happen with the floor slab? Is the floor slab holding the column or it's not holding? Is a gap between them? They're cast separately. So a very simple looking system suddenly starts to become very complicated if you start to think about every point on that one, right? And then the floor slab, if it is resting on the ground, it has a friction also. Or if it doesn't have a friction, the soil has settled. So many situations can alter this very simple scenario, just one column on the foundation and the piles. So, but like I said, engineers seem to be blind to all of that. They just bring the column down, put a line, tick, 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 hashes there, and call it fixed. Or if they put a pin, triangle there, put a circle there, and pin. But the reality is, as you can see, complex. And even for simple cases, it's not simple. So far, what we have seen is that bearing capacity is a function of footing size and vice versa. Loads on the foundation depend on how foundations are modeled, and foundation settlement should not be pre-specified, and modeling of basement is a tricky business. That's what we have learned so far, right? Okay, let's move one more step. Next one. Dynamics. Things are not linear. They are neither static. The structure is moving, the soil is moving, the ground is moving, the soil is deforming, the structure is yielding. Everything is in motion and is not linear. So how do you do that? So all of these can be converted into what we normally call is a spring damper dashpot system, or a nonlinear damper and spring system, linear spring system. So if you model the foundation in each direction by a combination of a damper, a spring, and a nonlinear gap or nonlinear element, then you can model all of the complexities that I mentioned to you, because you can model separation, you can model the contact, you can model the dynamics, you can model the yielding, you can model this nonlinear soil behavior or this nonlinear link. So if you have the data from the geotechnical people and you have the time and the capability, you actually can do pretty much lot with the foundation and structure. But this is still not enough. And I will tell you later why. Because we are still treating the soil as a structural kind of a material, but soil is not that. Soil is far more complex than that. Soil's this PY curve, which we've got, is not independent. They also depend on how this is there. So it's far more complex than that. But hardly any commercial software does it well, completely. Okay? But anyway, let's move on. Okay, now let's come to the interesting. These are the models from real buildings, real structural engineers who are very famous, have done tons of buildings everywhere. So it's not just class project that somebody didn't do that properly. Look at that the person, whoever modeled that thing on the top, which has nothing to do with structural design or anything. It shouldn't even be there, because that's not part of you're doing a structural analysis. And the person has modeled many, many small openings, gone into trouble. Why? Because the CAD model was like that. They imported it from the CAD model. So every detail come in and they model everything because it's so easy. But look at the foundation. Because foundation were not part of the CAD model, nothing came in, and he just put the fixed line over there and forgot about it. There's a foundation and a soil below that because the architect didn't put in their model, and the structural engineer also didn't bother to think about it. So on one extreme, you have this, another extreme, you have all of that. This is another extreme, that these are outside the structure, and that small opening has nothing to do with any structural response, but the model is there. Even small things, details, the engineer has modeled. But look at that, all the details. So many openings, nothing to do with that. It's just nothing. It's outside the structure. And look at the foundation. Just put the pin there. Okay. So this is the level of detail that engineers on one side do, which has absolutely no significance whatsoever on the structural response, and miss, which has this big significance on the structural response. And these are real structures, real buildings taken, from all the projects that we get to do. So I hope that our graduates will not be doing this when they go back. And we looked at all these buildings, hundreds of buildings, and we found the same issues everywhere. Okay, coming now to the more serious and slightly more difficult problem of dynamic response of buildings to earthquakes and soil foundation structure interaction. So now we are going below that. We are not just saying that if the foundation is there, we are actually looking at the soil also and seeing how this whole thing happens. So this is one of the theses that was done a couple of years, 5-6 years ago, from one student from Sri Lanka, Abhi, and she looked at how this soil, a tall building, and the soil all the way to the bedrock, what will happen if we model everything, not just by springs, but we just went all the way to the finest, not the finest, but the most level that we can go within reason. So this is a nice and the document as a reference to do that. Soil structure interaction is covered in this one very well, much more detailed than I just mentioned to you. So let's go into this one now. So general soil effect is like this. We cannot, for earthquake especially, the idea that the earthquake is hitting the structure at the foundation is actually not right, because the ground motion is traveling through bedrock. It doesn't travel through anything. So it's traveling through bedrock from one place to the other. So wherever it is, the bedrock, however deep it is, that's the one that is actually moving. So when the bedrock is moving, it may be very far. So when that will move, first of all, this motion has to be transmitted through the soil layers up to the foundation bottom. And then the foundation will move based on what the soil is moving at that level. So there is a change between the ground motion, between the bedrock, and while it reaches this one. And the building codes try to account for this by soil factors in their seismic load calculation. You might have seen, it's called SF or something. So it varies between 1 to 1.5 or 1.8, depending upon the soil, magnification of the ground motion due to the soil effects. So if it's directly rock, it won't be. But if something else in between, then this motion may be magnified. Okay. Or dampened, either way. So this is the code-based approach to soil. So if this is, you can see soil type A, B, C, D, and E. So the response will increase in certain ranges significantly from the base solid rock type. So the acceleration, observed acceleration, or the spectral acceleration at the foundation base will be higher than the acceleration at the bedrock. Okay. So that for the same displacement level. And that is normally soil type generalized curves are made through analysis. But each site is unique. If you are really doing the real soil structure interaction, you may have to go beyond that. Okay. So now let's see what happens to a simple building on a response spectrum for using various soil conditions. So that is the fixed base assumption. Natural period will change, because the first thing that will happen to a structure is, if you don't model the soil and you use fixed one, the base is very rigid. So your structure becomes rigid, your natural period will be shorter. If you put the soil model into that one, the overall the system stiffness will reduce and the natural period will become longer, because now the building is rotating and also deforming, and the soil is also rotating with that and deforming. So it's not fixed anymore. Soil can move and deform and rotate, so the natural period will increase. So this is the effect of just fixed base. The natural period is here, and then for stiff soil springs, the natural period is already increased, and for a very soft spring, the natural period is further increased. It seems like a good thing, because on the response spectrum, the force generated is now going to reduce, because the structure has become softer. So now it will attract lesser seismic force, because the natural period is increased. And the response spectrum is a relationship between the natural period and the force attracted by the structure from the earthquake for a given spectrum, right? So in one direction, it's a good thing, because if you include the soil, you will actually get smaller seismic demand compared to if you don't do it, because of the change in the natural period. Okay, because it now becomes softer, so it has a way to kind of sway and let the earthquake pass. So that's the first interesting thing. And very soft spring, so you can see almost half of that, or less than half of the force, will be experienced by the structure. So you may be overestimating the seismic demand if you use the fixed base. And some people might think it's a good thing, but there are other things which are going to be the other way. Okay. So now this is the low-rise and soft soil, high-rise soft soil, and low-rise fixed base and high-rise fixed base. So let's see what happens to them. So low-rise fixed base is here, and then low-rise soft soil will be here. You can see the others are over here, the long ones. So for tall building, it didn't matter. Those two you cannot see clearly. Those two lines are here. High-rise, the natural period is already very long, 4-5 seconds. If you model the soil, the natural period will not change much, because it's already soft, unlike a small building. So for a very tall building, 50-story above, soil modeling will not change the natural period significantly. Once again, it depends on the soil type and depends on other parameters also. But in general, the effect will be much smaller than for a short building, because of the shape of this response spectrum. The drop is closer to lower natural periods and flatter on the higher natural period. After like 6 seconds, it's almost the same, doesn't matter. So too long anyway. 4 seconds, can you imagine 4 seconds? Is very long. 1, 2, 3, 4, 1 cycle. So it's too slow for earthquake to be. First, earthquake ground motion is extremely fast, like this one. So this structure is so slow that it won't respond to that ground motion movement immediately. So it will respond its own way. So soil will not change that significantly in terms of the natural period. But it will change a lot in terms of the tilt of the building and the drift of the building and stability of the building, because a small rotation at the base will amplify by a huge height, and then you can see even one small half a radian, a little bit. This one, the top will sway a lot. So if you model the soil, you will find the natural period may not change, but this drift and sway will change a lot. Deflection will change a lot. So now let's get into more detail. So soil structure interaction effects are of two types when we go to full discussion now. One is inertial interaction, and the second one is kinematic interaction. So inertial interaction is the flexibility period lengthening, as I mentioned to you. Natural period becomes longer, So that is that. And then foundation damping, because if the soil is soft, your damping is higher. So you have those effects on inertia on one side. Kinematic is that the base slab averaging and embedded effects. So, which I will show you later. What does it mean? These are the ones which are hard to capture. These are easy. By putting the soil spring, you can capture them as I showed you earlier. But these on the right-hand side are difficult to capture or even to understand. So inertial effects, as you can see from here, is easy. You have the springs over there now, so the initial period will change because the base is not fixed. So it's kind of quite clear. So inertia-driven forces, base shear is related to base moment. They are related to that one, so it will reduce. So flexibility, period lengthening, foundation damping, soil stress damping, radiation damping. So this all can be captured within the structural framework that we have by adjusting the damping and adjusting the initial period, all coming from the dynamic and the inertial effects. So this is well and okay. So they will alter the base shear, obviously, because if the initial period changes, like I showed you, the demand will change and base shear will change. So I also mentioned to you base shear and T, the effect of that with different factors. So this is just explaining what I already showed you in that slide in a little bit more detail. You can see that, when you read it. You can also read the paper behind it. So kinematic interaction is more complicated, and normally people don't do it and very hard to do. But I'm just explaining to you that how that can be done. So free field motion and then foundation input motion, they're two different things. The motion of the free actual natural and what is actually happening in the foundation, like I mentioned to you, are two different things. So we need to get one from the other. So kinematic interaction will be there, base slab averaging and embedded effects, which I will show you now. So this base slab averaging is the wave passage and lag coherence. It's this little bit high, too much detail. You don't need to follow everything because I don't think you will ever be doing that in your practical work unless the project is really of high value. So you have the embedded effects, and this is the, all of that. So because the first one is saying that where is actually the base of the foundation? Is it the bottom of the basement slab, or is it the height of the wall? Where is really ground motion coming to the structure from? Because structure is extending all the way from the top to the bottom, right? So that averaging of where it will be applied is this one. So this is what will happen for the modeling if you want to go all the way. And this is what we are saying, that the structure is here. So your foundation, and then between the foundation and the structure, you create links. And then you model the soil also, soil medium also. You don't just model springs to represent soil. You actually go and use finite element modeling of the soil also to a far enough area that you can capture what's going to happen in the soil and how the things are coming from soil to the structure and going from structure to the soil and the gaps in between and everything. So you don't assume anything. Springs are not really connected anymore. There's a gap and there are links there. And then, so now this is the direct approach that you model everything, soil element, foundation element, everything. And substructure approach is that you convert this soil into a bunch of nonlinear damper spring kind of stuff and then connect together. Okay? Because you do substructuring, that means you do the soil separate analysis, you get the stiffnesses and the properties, and then bring them back and then model them using the structural elements, right? So it's more of that approach, that you do two separate approaches and then bring them together. And that's what people have the capability to do. So doing the full one is pretty complicated. And this is what she did. So it's less understood how it happens. This, for example, springs there and all the way here. As I mentioned to you, the pile is stopped here, but along the length, there are springs holding it. Soil is holding it. So this whole propagation. So for this pile, the ground motion will be different at every level. Because it's going to normally the pile is resting on the rock. So from the rock all the way up, it's not constant. It's varying. So, but we don't know where to connect it. In fact, it's not actually very clear when you put the foundation in SAP or something, where do they really assign the ground motion? At the bottom of the pile or at the base slab or where? I am also sometimes not clear where they're actually doing it. Which point, either is the lowest point or is it the basement or where? So I think that's still unclear where the ground motion is actually applied, or maybe they apply components on each of the nodes. I need to check sometimes what doing there. So finite element of soil is rarely performed in real design. So I'm not expecting anyone to do that, but you should know that how complicated the problem is that we have solved for research. It is done, like this one was done as a research project. So if somebody wants to do for research, they can still do it. I put the question mark here. According to the guide, it says that the trend is moving towards increased soil structure, but I don't see it, honestly. In 45 years of my practice, I haven't seen much change in people's mind on two things. One is soil structure interaction. Second is modeling of the masonry walls. Most engineers still ignore the masonry walls in their structure. They use the bare frame model, especially for small structures. They think it doesn't matter, but it matters so much. And still people keep ignoring it. And this is the second one. So this is her research was on this building. And then I'll just present you some of the things. So she made many models. She made model number 1. She made the code-based approach. She made all these models, model 2A, model 2B, this one with that one. So it put a whole dashboard. So create a basement and create around that another basin to contain the structure, and just put the soil model in between that, because you cannot model the soil indefinitely. So you create a basin around that, and in between you compress the soil and put it like that. Okay? And then you have the whole thing, 3A and 3B, go all the way down and actually go to the bedrock and apply the ground motion to the bedrock and see how it moves up to the soil, to your structure, and do the whole thing. Okay? So that's what she did. So the rest is a lot of details. She performed linear time history here, nonlinear time history over here, bedrock, ground motion, 3D models, a lot of work, a lot of work. And and then compare the results from there. So took many ground motions, tried to apply all the way and to the soil. This is and after all that work, so put the gaps over there, like this one, as you can see here, model around that, model the whole soil, locked it there, and then model the building. So it's a complete model of the building, of the foundation, of the basement, of the soil, with everything that the highest level of modeling, you can do. And it is not common for a tall building to do that. So that's the model, that's how it looks like. And then you got all the results from there. And surprisingly, we found something that wasn't completely expected. First of all, for this particular building, this particular soil, we didn't find a big difference between modeling everything and modeling between the three models. The difference wasn't much, okay? Except for some things. So, for example, in shear and moment wasn't so much. Shear, you can see we got differences, substantial differences at some story levels, and some was matched. And then story, this one also, you can see from here that the story response along the time, we also found differences that did not match the maximum shear in a story from the same ground motion with different models did not occur at the same time. So there are differences like that because the ground motion is not arriving at the same time. But in the end, the total result was, some of the results did not matter much and some mattered a lot. So different models on that. Dynamic behavior can be modeled. The effect of the nonlinear modeling of soil increase does not have major impact on response. This is one observation, that actually we found that all that effort did not produce a significant difference between the simpler models and the detailed models. So even if we consider all the effects, in the end, for the tall building, the difference was small. And one of the key reasons that we found is that the structural stiffness is already too soft. So the soil changes did not impact that much. But if the structure was very stiff, the difference was small building, it will be much more significant. Like let's say nuclear power plant or something like that, they will be much more significant. And because the structure is so soft that what happened in the foundation, it kind of gets absorbed. So now we have that you can do all of that, but maybe you don't need to do the last one. Okay. So we also wanted to sort of find out that you really need to do that or not? And the conclusion was not really. It's good enough to do at least the minimal soil structure interaction using springs and all. All right. So the decision whether we include the soil structure or not is something that people always think about. And like I said, my feeling is that the minimal soil interaction should be included in any case, right? Because it doesn't cost you anything else. It's just put the foundation there, also put the soil there. Don't ignore. You're modeling everything, and there's a column below that. There's a huge raft. How can you ignore it, right? Or there's a footing. How can you not see it, right? So don't just stop at the base of the column. Go down and go at that, and then just replace the soil by springs and in some case nonlinear elements and some whatever. Okay. All right. And this is very significant for other structures like bridges. Absolutely has to be done because bridge is not tall, not like so their natural period and the soil natural periods are almost the same. So it is very important in the bridges, especially in the abutment, to do that. Almost, you should not go without that. And embedded structures, nuclear power plants, there's these structures of high value. This will be quite critical. Okay, so we just stop here.